So in this lecture, I will discuss chemical bonding, the different types of chemical bonds. Then I'll look at Lewis structures and then discuss a little bit on resonance. So basically, a chemical bond is a strong attractive force that holds atoms together in molecules and ions. The formation of a chemical bond usually involves the outermost shell electrons of atoms. Now, there are two different types of chemical bonds. These are ionic bonds and covalent bonds. The electrons that are involved in these chemical bonds are usually called valence electrons. So let's look at ionic, or sometimes also called electrovalent bonds. So an ionic bond is formed between two atoms when one or more electrons are transferred from the outermost shell of one atom to the valence shell of the other atom. So the atom that loses electrons becomes a cation or a positive ion, and the atom that gains electrons becomes an anion. Sometimes the cations, some people call them cations. Okay. So in this type of chemical bonding, one thing that should be clear to every student is that here electrons are lost and also electrons are gained. So one atom will lose these electrons and there's another atom that gains them. So there is the formation of a positive ion and also a negative ion. Now, after that happens, there is an electrostatic force of attraction that will occur between these two ions. Remember, we have generated a charge, so we have a positive charge and also a negative charge. So this type of bonding occurs easily because between the elements of low ionization energy and also alkali earth metals, and also the elements of high electron affinities, for example, nonmetals, halogens, and also oxygen. Now, metals are rather elements of low ionization energy, like the alkali and alkaline earth metals. It means that they easily lose electrons, and therefore the amount of ionization energy that is required is very, very low. That is to remove the amount of energy that is required to remove an electron from the outermost shell when the element is in gaseous state. So an example of ionic bonding is seen between sodium. So sodium has got one electron in its outermost shell, which it can lose, whereas fluorine has got 7 in its outermost shell. It requires 1 electron to reach its octet state. In this case, sodium will lose an electron to become a cation with a positive charge. This is to indicate that it has lost 1 electron, whereas fluorine would have gained 1 electron with a minus charge. So the product, therefore, will be sodium fluoride. The second type of bonding is covalent bond or covalent bonding. In a covalent bond, compared to an ionic bond, here there is sharing of valence electrons. Now, what will happen here is that the electron is not owned by any of the two atoms that share it, but it's just shared between the two. So again, here the octet rule applies. The shared electrons will make the two atoms reach their octet state. For example, here, hydrogen, 2 hydrogen atoms will share an electron, and will have an octet number of electrons equivalent to helium. Two chloride atoms, will actually share an electron, and therefore will have an octet state of electrons. An octet state of electron is either 2 or 8 electrons in the outermost shell. So for chlorine, this chloride atom, this side, you have 2, 4, 6, and 8 electrons, the 2 being the ones shared. Even this one will have 2, 4, 6, 8 electrons in the outermost shell, and then it will achieve an octet state of the noble gas argon. For nitrogen atoms, so nitrogen has got 5 electrons in its outermost shell. It's requiring 3 to reach an octet state. So with another nitrogen atom, it will form 3 shared bonds to form a triple bond. And then you have 2 electrons this side. So 6 shared plus 2. For each one of them, you have 8 electrons being shared. And then this one will also achieve an octet state, which is similar to that of neon. So the formation of chemical bonds, really, like we have said, is in 2 extreme forms. Ionic bond, where there is complete transfer of electrons from one atom to another. Then covalent bonds, here we have got electrons that are shared between atoms. So most bonds are somewhere in between these 2 extremes. Here we have just a snapshot of the periodic table, just to show the valence shell electrons. So the group 1A elements will have 1 electron in the outermost shell. Okay, so like hydrogen and lithium. Group 2A, beryllium has 2 electrons, and its configuration is given there. So you have 2s2. Then for boron, you have 2s2, 2p1. Okay, so again, here what is important for you to take note is that the outermost shell electrons are those in those orbitals. So for boron, you have 2s2, or rather in the s orbital you have 2 electrons, and in the p orbitals you have 1 electron. So an example is given up to group 8, which is actually the noble gas configuration. So here we are saying number of valence electrons is equal to the group number. How do these bonds form? So a bond can result from a head-to-head overlap of atomic orbitals on neighboring atoms. One thing that we have to take note here is that this type of bond formation, which we are indicating, is just to show exactly how these electrons are shared, or these electrons form up these bonds. So for example, in HCl, you have hydrogen and chlorine. Ideally, this electron would be lost if this was an ionic bond to chlorine. Okay, so the hydrogen will have its electron in the 1s orbital. The chlorine will have its electrons in the 2p orbitals. Okay. Now, the valency shell electrons for chlorine, there are about 7 of them. So any one of the 7 can form this overlap. So this type of overlap places bonding electrons in what is called a molecular orbital along the line between the 2 atoms and forms a sigma bond. So here a sigma bond is actually a bond that results from an overlap of orbitals head-on. So a head-to-head overlap of orbitals results in a sigma bond. So this head-to-head can be between an s orbital and a p orbital, or between 2p orbitals. Okay. So what we're showing here is the px and the px orbital can overlap head-on, meaning that that is going to form an overlap by hitting straight on, and you have this type of orbital. Or you can have an overlap occurring at the center here, and then the two being the initial orbitals. Or it can actually be sideways, but head-on. So you have the py, which is in the more or less like vertical orientation. So here you can still have a sigma bond forming where these are more or less like standing, and then they will form an overlap as indicated there. Okay. So the electron distribution is depicted with Lewis electron dot structures. So electrons are distributed as either shared or bond pairs, and also unshared or lone pairs. So you can have bond pairs or shared electrons, or you can say these are unshared or lone pairs. So let's look at these types of electrons. So there you are shown a bond pair, which is the one that is formed between two atoms. So that is a bond pair. Then the electrons that are in the outermost shell, which are not involved in a shared bond, these are called unshared electrons or lone pairs. And usually they are in pairs. So like you have 3 pairs of lone pairs or lone electrons. So here we have 6 electrons, but we are calling them lone pairs. Now the structure that is drawn to indicate the shared electrons and also the lone pairs is known as a Lewis electron dot structure. So the lone pairs are shown in pairs around the atom of interest, and then the shared bond is also shared like that. So if you are asked to draw the Lewis dot structure, that is how you can indicate it. Okay, so a Lewis structure is a representation of covalent bonding using Lewis dot symbols in which shared pairs of electrons are shown, either as pairs of dots or as bonds between atoms and non-bonding electrons. Okay, so here the valency electrons on an atom is equal to the group number. That is one thing that we have to know. In terms of distribution of these electrons, they are distributed to ensure that each atom reaches its octet state. And therefore, just remember that the bond pairs are shown as a complete line, like that, as a dashed line. And then the unshared electrons, they are shown as dots like that, just to indicate that these are electrons. Now, what are the rules for drawing Lewis structures? First of all, sum the number of valence electrons for each atom. Okay. Second, decide the central atom. So the central atom is usually written first in the formula. So if, for example, you have NO2, nitrogen is the first atom that is written, therefore it is the central atom. Complete the octets of atoms bonded to the central atom. Remember that hydrogen can only have 2 electrons. Okay, so atoms tend to lose or share electrons until they are surrounded by 8 electrons. So that is the octet rule. So each time we want to distribute electrons around atoms, we have to bear in mind that each atom must be surrounded by a maximum of 8 electrons. But there are some who actually must have a maximum of 2 electrons, like hydrogen. So place any leftover electrons on the central atom, even if doing so results in more than an octet. So we'll see what the meaning of this point is. And then if there are not enough electrons to give the central atom, try multiple bonds. So for example, if we want to draw the Lewis structure for phosphorus chloride, the total number of valence electrons here, if we have to sum up, since we are starting with the summing up, for phosphorus, it's in group 5. So it will have 5 electrons in its outermost shell. So that is the one there. And then chlorine is in group 7. And we have 3 chloride atoms here. So 3 by 7. So we have a total of 26. Now, when we're drawing the Lewis structure, we said using these rules that first sum the number of valence electrons. So we have summed them. Number 2, we said locate the central atom, which is usually written first. So in the formula, the central atom is written first in the formula there. So we have phosphorus. So that is the central atom. So what we're going to do is just to write the central atom and then connect it to 3 chloride atoms. So that is 1, 2, and 3. Now, by drawing these 3 line bonds, the shared electrons would have been indicated. And out of 20, we have used 6 electrons. So 2, 4, 6. Okay, so we are out of 26, we have used 6 electrons. So we are remaining with 20 electrons. What do? We begin to place them around these atoms that are bonded to the central atom. So what's going to happen is that we are going to put 2 electrons on this chloride, another 2, another 2. So we're going to have 2, 4, 6, and 8 for this chloride atom. And we stop there. This one also, we put 6 more electrons, we'll have 8. Even this one, 6 more electrons, we have 8. Okay, so at this point, we have 8, 8, 8. 8 by 3 is 24 electrons. We are remaining with 2 electrons from the 26. Now, any leftover electrons, we have said here that place any leftover electrons on the central atom, even if doing so results in more than an octet. More than an octet is 8. So here, when we place the remaining electrons on the phosphorus, for us, it's not giving us any excess. Okay, we are actually exhausting them and having 8 electrons on the phosphorus. Okay, and that is the Lewis dot structure for this formula. If we are building again the Lewis dot structure for ammonia, first of all, we'll decide on the central atom. The central atom, again, just to emphasize, is never hydrogen. Secondly, the central atom is the atom of lowest affinity for electrons, meaning that it should not be drawing electrons just to itself. So in ammonia, again, here nitrogen is the atom that is written first. So it's the central atom. The next thing is to count the total valence electrons. So what we can do is just to add the total number of valence electrons by adding the group numbers of the atoms in the formula. Okay, so we can check in which group nitrogen is. It's in group 5. Hydrogen is in group 1. So if we add them, we are going to see that for hydrogen, we have 3 of them. For nitrogen, we have 1. So 3 times 1 plus 5, we will have a total of 8 electrons. Again, we'll draw the Lewis dot structure, starting with the central atom. So we are going to put nitrogen at the center and then bond it to 3 hydrogen atoms. Just by bonding these 3, we would have used 6 electrons. So we have formed 3 bonding pairs. Okay, so 3 by 2 is 6. From the total 8 electrons that we had, we are remaining with 2. So those extra 2, we are going to place them on the central atom. So those are the 2 that are remaining to make 8. And that will form a lone pair of electrons. So if you check, you find that each one of these atoms has got an octet state of electrons. So for hydrogen, it needs a maximum of 2. So it has 2 electrons in this bond pair. This hydrogen, 2 electrons, that hydrogen, 2 electrons. For nitrogen, it requires 8. So it has 2, 4, 6, and 8 for the lone pairs. So you have reached a lone, an octet state of electrons. So from this Lewis dot structure, we can see that we have 3 bond pairs and 1 lone pair. So we have 1, 2, 3 bond pairs and 1 lone pair. Okay. How do you draw a Lewis dot structure for the sulfite ion? Okay, so first of all, decide the central atom. The central atom is the atom written first in the formula. So we have sulfur as the central atom. The second thing is to count the valence electrons, in which group is sulfur, in which group is oxygen. So sulfur is in group 6, oxygen is in also group 6. So sulfur therefore have 6 valence electrons. Oxygen will also have 6 valence electrons. So the sum of the 2 will also include the negative charge. What does negative charge mean on an ion? It means that a compound or a group of atoms has gained electrons. If it is a positive charge, it means that they have lost electrons according to, or rather equivalent to the charge. Therefore, the total electrons will be 6 for sulfur, plus 18 from oxygen, plus 2 from the negative charge. Therefore, the total we're going to have is 26 electrons, or in short, 13 pairs of electrons. So we expect to put across about 13 pairs. Okay. Now, step number 3, you form sigma bonds. How do you form sigma bonds? You put the central atom at the center and then make covalent bonds to the 3 oxygen atoms. So here we are here. So we have oxygen, another oxygen there, and another oxygen here. What would have done by doing that is would have used 6 electrons, or would have drawn 3 sigma bonds. So 1, 2, 3. The 3 is 6 electrons. From 26, we are remaining with 20 electrons. The next thing to do is to place these electrons on the attached atoms so that they reach an octet state. And then the remainder, we're going to place them on the central atom. So the next thing to do here is just to put the electrons on the central atom and the other atoms of oxygen. So what we have here is 8 electrons on each atom, and then what we have here is that all these atoms have reached an octet state. So we have 8 for this oxygen, 8 for this sulfur, 8 for this oxygen, 8 for that oxygen. So due to the fact that all these have reached an octet state, then we leave them like that. But since this is an ion, you would do well to put the square brackets around it and put a -2 charge outside that bracket. For carbon dioxide, the central atom is carbon. Again, we count the valence electrons. For carbon, it's 4. For oxygen, it's 6. So 2 by 6, 12, plus 4, we get 16. So we expect to have 8 pairs. So the next thing is to place the central atom at the center, and then the remainder of the electrons, we place them around the carbon. Okay, so we here would have used 2 bond pairs. We are remaining with 6. So those remaining 6, we place the lone pairs on the outer atoms. So when we place the electrons on the outer atom, we are going to exhaust them. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8. So we have used all the pairs of electrons. But if you check, you are going to see that oxygen is in octet state. This oxygen is also in octet state, but the carbon is deficient of electrons because you have 2 bond pairs, and these 2 bond pairs are equal to 4 electrons. So we are short of 4 more electrons, and we have exhausted all the 8 pairs. So what you do is you're going to drop these electrons, the 2 pairs. So from here, donate these 2 so that they are shared, and these also donate. So what you are going to have is to form double bonds. So this is what we are saying. You move these 2 pairs to form a double bond, and also on that one. So what you are going to have is a double bond between these 2 oxygen atoms and 2 lone pairs on each oxygen atom. And so that is the Lewis dot structure for carbon dioxide. So the second bonding pair forms a pi bond. So a pi bond is formed due to an overlap of electrons or orbitals, sideways. So when the orbitals overlap sideways, they form what is known as a pi bond. So in a double bond, you have 1 sigma bond and 1 pi bond. In a triple bond, you have 1 sigma bond and 2 pi bonds. Okay. So the double and triple bonds are commonly observed for carbon, nitrogen, phosphorus, oxygen, and sulfur. So when you are dealing with these elements or atoms, you have to bear in mind that you can be able to form double bonds, triple bonds when you are forming these Lewis dot structures. So an example here, you have carbon forming a double bond with the hydrogen. Again, here you have sulfur forming a double bond with 1 oxygen, and then these other 2 oxygen atoms, it's a single bond. For sulfur dioxide, again, we can draw the Lewis dot structure. We follow the same thought process. The central atom here is sulfur, and then the outer atoms are 2 oxygen atoms. So the first thing we do is to sum the total of the valence electrons by adding the group numbers of the atoms involved in the formula. So for sulfur, it's 6. For oxygen, it's also 6, but we have 2 oxygen atoms. So we have 6 plus 2 times 6, we have 18 electrons to distribute on these atoms. So again, we write the central atom and the 2 oxygen atoms, which are the outer atoms, distribute the electrons so that they are all exhausted. Again, when you look at the distribution here, we have used all the 9 pairs. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And yet sulfur is deficient of 2 electrons. So we'll do what we did for carbon dioxide. We can drop this pair of electrons here so that this sulfur reaches an octet state, or we can drop this pair of electrons there so that we have a double bond there, okay? So what we are going to have there is, here we have an issue of O. It's not to drop both of them because you have more than the octet state. So you decide to just drop one pair, okay? So what you're going to have is one oxygen having a double bond. So in this case, you have 2, 4, 6, 8 electrons for sulfur. So it's in an octet state. So that is the Lewis dot structure for sulfur dioxide, or you can draw it in this manner. Or if you like, you can draw 2 double bonds on sulfur as indicated or as shown for carbon dioxide. So you have 2 double bonds here, and then these 2 oxygen atoms will have 2 lone pairs on each one of them. Okay. And then all of them will have an octet state. So these structures that have almost the same distribution of electrons around the same atoms, these are called resonance structure. So the proper Lewis structure is a hybrid of the two, meaning that if we were to draw the two here, which are represented, we might just indicate that you can actually put the double bond either this side or that side. So that becomes a hybrid. Okay, so the hybrid can be shown like that below here. For urea, if we have to draw the resonance, or rather the Lewis dot structure, we indicate the sum of the valence electrons. In this case, it's 24 electrons. You can do the calculations now that you are familiar. The next thing is to draw the sigma bonds. Again, here, for you to identify the central atom is written first in the formula, so that is carbon here. These here are in brackets, okay, meaning that there are 2 of them bonded to that carbonyl group. So you have the carbon and the oxygen indicated there. The next thing is to place the sigma bonds around the central atom, and when we do that, we would have used 14 electrons or 14 pairs of electrons, which subtracted from the 24 leaves us with 10 pairs. So we're going to place them around each atom which is not yet at octet state, so that we can exhaust these electrons. And if you check from here, you have nitrogen still deficient. This nitrogen is still deficient. This carbon is still deficient, and that oxygen. So make sure that we distribute these electrons around these atoms. So the first thing that we are going to do is to introduce a double bond between carbon and oxygen. And then we place the lone pairs on oxygen so that we have an octet state, which we have done there. The next thing is to place the remaining ones also on the nitrogen atoms. Okay, so remember that we were remaining with 10 electron pairs. So we have 1, 2, 3, 4, and 5. Okay, and then we have exhausted all the electrons. Now, it's not always that you're going to have a perfect Lewis dot structure. We have situations also where certain compounds or certain atoms violate the octet rule. And the octet rule is that you have a maximum of 8 electrons around an atom. Now, this usually occurs with, for example, boron. So boron trifluoride which is drawn there, and also sulfur tetrafluoride. So if we look at boron trifluoride here, the central atom is boron. Count the total number of electrons. You have 3 for boron and 7 for fluoride, because it's in group 7 times 3, you have 24. If you assemble the electron dot structure, what you're going to have is 8 electrons for this fluorine, 8 electrons for this fluorine, and 8 electrons for this fluorine. Boron also will have 2, 4, 6. And boron, since it's in group 3, it would have actually assumed an octet state. Okay, so if you check on it, you see that boron has a share in only 6 electrons or 3 pairs. In many molecules, boron is electron deficient. Okay, so what then is the issue? This man is confused here. Okay, what if we form a boron fluoride double bond to satisfy the boron atom? Now, what is going to happen is that if we satisfy the boron and calculate the formal charge for each atom, we are going to actually find that the fluorine on top will have a formal charge of +1. The fluorine, the second fluorine here, or rather, if we calculated for boron before the other one, we'll have boron to have a formal charge of -1. Okay. So to have a +1 charge on fluorine with its very high electron affinity is not good. So negative charges are best placed on atoms with a high electron affinity. Now, electron affinity is the power of an atom to draw electrons to itself. Ideally, fluorine draws electrons to itself. It doesn't give away electrons. And this is why we're saying that it is not a good thing that fluorine should have a positive value, just like boron. Boron cannot have a negative value because boron being in a group 3, it actually releases electrons, it loses electrons. Okay. So to conclude on this one, it means that the structure, the Lewis dot structure for boron trifluoride would be this one indicated here, where all of these have reached an octet state, but boron remains deficient of electrons. Another example is sulfur tetrafluoride. The central atom is sulfur. Again, if we do the electron addition, the sum is about 34 electrons, equivalent to 17 pairs. Again here, sulfur, if you indicate all the electrons, sulfur here will have an excess of 2 electrons. Instead of having 8 electrons, to have 10 electrons, which are around it, forming 5 bond pairs. So the 5 pairs around the sulfur atom is a common occurrence outside the second period. So most of the atoms in the second period tend to deviate from the normal octet rule. Let's look at formal charges. So atoms in molecules often bear a charge which is positive or negative. Now, to calculate the formal charge, you're going to have the group number minus half the number of bond electrons minus number of lone pairs. So the group number of the atom minus half the number of bonding electrons. So those electrons in a bond, when you count them, half that number, and then minus the number of lone pairs. So the most important dominant resonance structure of a molecule is the one with formal charges as close to zero as possible. So if you are given three structures to determine which one is the most dominant resonance structure, it is that structure which, when you add all the formal charges, it will give you a number which is close to zero. Okay, so here, for example, we're saying draw the, okay, so formal charges, the number of valence electrons in the isolated atom minus the number of electrons assigned to the atom in the Lewis structure. So these are not real charges, but help with keeping count of electrons in Lewis structures. They're about formal charges. So the question is, draw the Lewis structure of NO plus and determine the formal charges of the atoms. Which Lewis structure is the preferred one? So number of valence electrons is equal to 11 minus 1, which is equal to 10. Now, why are we saying 11 minus 1 is equal to 10? So if you count here, we are saying minus 1 because this plus means that we've lost an electron. But if you count the for NO, nitrogen is in group 5. So 5 plus oxygen is in group 6. 5 plus 6, it's 11. Then we're saying minus 1 to account for the positive charge, which is given there. So we have 10 electrons. So when we draw, we begin just to shuffle around these electrons. Okay, so between nitrogen and oxygen, we can form 3 double bonds. The 2 lone pairs, we put them that side. Here again, we can try to put 2 electrons, and then the lone pairs, 1 lone pair on nitrogen, 2 lone pairs on oxygen. Again, we just shift. So the most important thing is that when we are drawing the Lewis dot structures, we are not interested in drawing an octet state. We are just shifting the electrons around. Okay, so after doing that, then we can calculate the formal charge. So we are saying the formal charge is the group number minus half the number of bond pairs electrons minus the number of lone pairs. So if we check for nitrogen, we are saying nitrogen is in group 5. So group number is 5 minus the bond pairs are 1, 2, 3. So minus half the number of bond electrons, sorry. So that is bond electrons. So here we have 5 minus, in brackets, if you like, half times the number of bond electrons. These are 6. So half of 6 is 3, minus again the number of lone pairs on the atom. Okay, so now we have 5 minus 3 minus 2. Okay, so 5 minus 3 is 2. 2 minus 2 is 0. So this is where we're getting this 0. For this oxygen here, again, we are saying group number minus half the number of bond electrons minus lone pairs. So group number for oxygen is 6. The number of bond electrons is 6. As you can see here, the bond electrons are these that are bonded to another atom. So 6 minus the lone pairs is 2. So we have 6 minus half of 6 is 3. So 6 minus 3 minus 2. So we have 6 minus 3 is 3. 3 minus 2 is 1. So we have plus 1. That is the plus 1 here. Okay, I hope you are following how I'm calculating these formal charges. For this nitrogen, again, the group number is 5 minus half the bond electrons, half of the bond electrons, these are 4. So half of 4 is 2. Then the number of lone pair electrons is 2. So we have 5 minus 2 minus 2. So minus 2 minus 2 is minus 4. 5 minus 4 is plus 1. That is the plus 1 here. For oxygen, group 6 minus the number of bonding electrons, we have 4. So half of 4 is 2. Then minus the lone pairs, that is 4. So minus 2 minus 4, that is minus 6. So 6 minus 6 is 0. So that is the 0. I'm sure you can do the calculations for the other ones. Okay. Now, the structure that is the most dominant Lewis structure, we have said it is the one that has got the lowest charge. Okay. So when you look at these structures, we are saying structure 1 is the preferred because the positive charge is on the least electronegative atom. So here between nitrogen and oxygen, nitrogen has got a higher, okay, so here what we have, okay, so that is our structure 1. So oxygen has a 0 charge, and the positive charge between nitrogen and oxygen is on nitrogen, meaning that oxygen is more capable of drawing electrons to itself than the nitrogen. So the atom that has got the least electronegative charge should be given a positive charge. So this example again is you have this structure. Again, if you are asked which one is the most predominant Lewis structure, what you do is just to calculate the formal charges. I've indicated earlier on how you can calculate these formal charges. So after the calculations, if you like, you can just go through and pause this video as you are calculating these formal charges and make sure that you come to these numbers which are indicated here. After the calculations, you see that structure 1, which is this one here, is preferred because the negative charge is on the most electronegative atom with the lowest formal charge. So the lowest formal charge is nitrogen here with a -1, meaning that in this structure, it will tend to draw electrons more to itself due to the fact that it is highly electronegative. Now, tutorial questions here, if you like, you can just try to go through them so that you can acquaint yourself with what we have been doing. But just to show exactly what we were doing, if you were to draw the resonance structure for carbon dioxide, what you would have really is a hybrid. Okay. If you drew it like this, you would have a positive charge on one oxygen and a negative charge, but carbon dioxide will have a charge of 0. Okay, so which resonance structure would be predominant between those structures? What we have is the form without formal charges is better. So no negative charge or no positive charge on the oxygen, because oxygen cannot have a positive charge. So that would be the best structure. So for writing Lewis structures, again, you can go through these problems just to see how you can draw these Lewis structures. But when you just follow the steps, you'll find that it becomes easy to draw them. Okay, so write a Lewis structure for carbon CO2 F2. So one of the compounds responsible for the depletion of the stratospheric ozone. So the steps is 1, carbon has the lowest electronegative value and is the central atom as indicated there. The other atoms are placed around it. So the total number of valence electrons in this compound is 32. So make bonds and fill in the remaining valences. Okay, so if we did that, we would have a structure like that. Okay. Another question is write the Lewis structure for methanol. Again, we're going to follow the same thing. Hydrogen can have only one bond, so carbon and oxygen must be next to each other, with hydrogen filling in the bonds. The total number of valence electrons in this case is 14. Again, we just place them like that. So that is the structure, the Lewis structure. Okay, so we have the bond pairs, the lone pairs on the oxygen, and the hydrogen bonded to oxygen. Another example, I think, is if you are asked to draw the structure for ethylene and also nitrogen. So the solution is for ethylene. There are 2 times 4 plus 4 plus 1 valence electrons. So what we have here is 2 carbons to give you 8, plus 4 hydrogens to give you 4. So 4 plus 8 is 12 valence electrons. So if you draw them like that, you have 1, 2, 3, 4, 5 bond pairs. You are remaining with 1 pair. So it means that you're going to need to form a double bond between the 2 carbons. For nitrogen, you have 2 nitrogen atoms in group 5, so you have 10 valence electrons. Therefore, a triple bond is required to make an octet state. So if you distribute the lone pairs around the nitrogen, you find that if you place 2 double bonds, rather a double bond between the nitrogen, you still have a situation where the 2 nitrogens will not be in octet state. So the preferred Lewis structure is one that has 3 double bonds and a lone pair of electrons on each nitrogen. We can also show electrons which are delocalized in a Lewis structure. So delocalized electrons means that these electrons can actually, because these are in orbitals, they can move around. Okay, so instead of having a static bond, you would have a situation where it is possible to form either type of bond. So in this case, the double bond between this structure of ozone, you can have it between this oxygen and that oxygen, or it can be on the other side. Okay, so neither structure is actually correct but can be drawn to represent a structure which is a hybrid of the 2. So a hybrid of the 2 Lewis structures is called a resonance structure. So a resonance structure is drawn with dotted lines around where the double bonds can form. So like the way this is indicated here, that's how you can draw a resonance structure. Okay. So it can be given to draw, for example, the resonance structure for the nitrate ion. Okay. So again, you just start with drawing the Lewis structure, put the electrons around the outer atoms and also the central atom, and then afterwards ensure that each atom has got an octet state. Now for the nitrate ion, remember that we have a negative charge, meaning that we have gained 1 electron. So that is why here we have 5 plus 3 times 6 plus 1 to give us 24 electrons. Please do not forget, if a compound has got a negative charge, you include that negative charge. If it's a negative, it's plus 1. If it's a negative, it's plus the number of electrons indicated by the charge. If it's positive, it's minus. Okay. So what we have here is just a distribution of the valence electrons on the nitrogen and the oxygens. what we do here is that you can see that nitrogen is deficient of 2 electrons, so we can give it 2 electrons from this oxygen. We can also decide to give it 2 electrons from the oxygen above here, so to form a double bond. We can also decide to give it 2 electrons from this oxygen below here to form a double bond. Therefore, our hybrid structure will actually involve formation of a double bond either this side or that side. Okay, so that is how you can show the resonance hybrid. So the formal charge can be used to select the best resonance structure. So basically the formal charge is the charge an atom would have if the bonding electrons were shared equally. So we have already done how to calculate the formal charge. We said that is the group number minus the number of the lone pairs plus the unshared electrons. So for oxygen A, you have valence electrons, they are 6. Non-bonding electrons, they are 4. So here, this A, you have valence electrons because oxygen is in group 6. Non-bonding electrons, they are the lone pairs 1, 2, 3, 4. So that is the 4. Bonding electrons, they are 4 also. So 1, 2. Okay. So 1, 2. So half of that, so 4 times half is 2. And therefore the formal charge is equal to 0. So this is the same as what we did earlier on, except here, instead of saying minus minus, we have just said add the 2 and then subtract from the valence electrons. So valence electrons is 6, and shared electrons, which are the lone pairs, these are 4 plus 2, that is 6. So 6 minus 6 is 0. So that is the formal charge there. For B, number of valence electrons is 6. Non-bonding electrons, there are 2, which are the lone pairs. So those are the ones indicated there. Number of bonding electrons. So this oxygen is bonded to this oxygen via 1 bond, 2 and 3. So 2 by 3, that is 6 electrons. So half of 6 is equal to 3. The formal charge is equal to +1. This is because you have 6 minus 2 plus 3, which is 5, and you have a +1 charge. For oxygen number, oxygen 6C, so oxygen C here has valence electrons is 6 minus the unshared electrons are 1, 2, 3, 4, 5, 6. They are 6 plus half of the bonding electrons. Bonding electrons is 2. So 2, or rather half of 2 is equal to 1. So you have 6 minus 6 plus 1, which is 7. 6 minus 7 is minus 1. Okay, so that is the formal charge. So 3 criteria for choosing the more important resonance structure. Smaller formal charges, either positive or negative, are preferable to larger charges. Avoid charges like plus plus or minus minus on adjacent atoms. A more negative formal charge should exist on an atom with a larger electronegative value. Okay. An example, you have NCO has 3 possible resonance forms like that. If you calculate the formal charges on these structures, you are going to get those formal charges. You can do the calculations if you like. So forms B and C have negative formal charges on nitrogen and oxygen. This makes them more preferable than the A. So you can see that they have got a negative charge on nitrogen and the oxygen, which makes a little bit more sense because these 2 atoms have a higher electronegative value than the carbon. And then we're saying form C has a negative charge on oxygen, which is the more electronegative element, before carbon contributes the most to the resonance structure. So if you like, you can also go through these formation of these resonance structures and see if you can be able to locate which one has a beta resonance structure. And the beta resonance structure must have a negative charge on the more electronegative element, so that it would make more sense. So basically, that is the end of this presentation on formal charges and also Lewis structures. Thank you very much.